So this video is kind of an opener for section 2 of chapter 11 for biology. In this section, we're going to talk about different kinds of selection and how they act on a distribution of traits in a population. So I have a couple other videos that I'm also going to attach that were made in the past, but I had to have a little intro here so that we could talk about that normal distribution. So right away in your notes, normal distribution is a bell curve. I don't know if you've heard about that before, but you would understand what it would look like and how it would apply. So a normal distribution, you need a picture of normal distribution in your notes somewhere. Let me move this up real quick. So just off to the side somewhere so you understand what it would look like, right? When I'm drawing these graphs as we go through the notes, so don't put this in where there's directional selection or stabilizing or disruptive. We'll do that later. But when you're talking about a distribution of traits, this normal distribution, right? When I say bell curve, I mean something that looks like this, right? And that's not perfect. It's supposed to mirror one side or the other. But the idea is that if you have a number of organisms that have given traits, right, that exist on a continuum some way, somehow. So we could talk about this in a lot of different contexts. We could talk about heights of students in your class, right? So if I take one class in particular, fifth period, right, not to be mean to anybody because this doesn't mean anything in this context, but on the short end of the spectrum, we might have someone like Brenna Hag, right? No offense, Brenna. But on the other end, right, Tyler Johnson's also in that class, right? And he's pretty dang tall. He's over 6 foot. But most of you guys fall somewhere in the middle, which is why this graph is highest in the middle, right? So our average class height may be somewhere in between those two. And most of us are somewhere in between those two. There's only a few people that are over 6 foot tall in your class. And there's only a few people on that shorter end of the spectrum, right? Shorter than 5'5" maybe. But most of you would fall somewhere in between. That's the idea of this normal distribution, right? The average is right in the center, and there are more people that are average height than those that are tall or those that are short. Right, so we're going to talk about a normal distribution a lot, but we're also going to talk about microevolution, an observable change in those allele frequencies of a population over time. So if we were to look at a classroom from not today, but maybe 100 years ago in this country, right, in a high school, right, everyone across the board would be a little bit shorter, right? Our population in general is getting taller and taller and taller. If I was to superimpose that older population, that other generation in here, right, their average height might be an inch or two shorter than our average height now. So we can tell that this population is changing over time, right? We're getting taller. Why are we getting taller? It depends, right? A lot of that probably has to do with nutrition, right? Better nutrition, you're going to grow taller, just like a plant's going to grow taller when it has better soil. But generally speaking, we can track change in populations when we're looking at a distribution of traits, and that's what everything we're going to talk about in this section comes from. So we could use that example in a lot of different ways. Again, a bell curve, one of its main usages is actually in grading, right? So if you go to college someday and you hear a teacher tell you that they're going to grade you on a bell curve, I would suggest that unless you're lazy, you might want to run for the hills, because the original usage of this, or one of the original usages of this distribution curve, is to grade people, right? Average is a C. Only a few people in every class should get an A, and a few people should get Fs, right? And then you have other grades in between, obviously. But essentially, if a teacher told you that they were going to grade you on a bell curve, that means that you could get a 96% on your test and still get a B, because there are too many people that were better than you that should be considered that A standard. So if you're graded on a bell curve, you're not graded based off of just the grade itself. It's how good did you do compared to your peers. Because if more than half of your peers did better than you, even though you got a 96, you're still going to get a C. So that's why I would say run for the hills. I didn't want to be in that class either, because that's not necessarily fair, right? Because in college, you're expected to be in a class with a lot of people that are just as smart as you are, if not smarter. Otherwise, other contexts, well, in terms of change, right? Again, if you were in that college class, assuming you have peers that are trying really hard and they're studying and everything else, right? There are a lot of things that could factor in on this distribution, right? If everyone in the class was to study, right, that should shift more towards that A side, right? There'd be more B's than C's instead of most of the students in class getting C's. Whereas we could also flip that, right? Maybe you like to procrastinate. Maybe you're not good at preparing, right? You could also have a negative shift, right? You could have a lot of students in a class get D's and less C's than D's, right? So I would suggest that you probably study, but if it was the case where an entire class was to procrastinate, you might see a shift in a different direction, right? Again, we're just looking at the change. How is the new population different than the original one, right? So looking at a grade scale, a normal distribution for grades is not a bad thing because it can tell me something. If I see that red line as opposed to the black or the green, right, that might also mean that I'm not doing a very good job of teaching you guys, right? So I would want to know that, and I'd hopefully change that. Whereas if I'm seeing that green line, I know that there's probably not an information problem. You're learning what you're supposed to learn. In fact, you're exceeding. So there's purposes for that, but I would never grade you on a curve, on a bell curve, because it's just not fair. You shouldn't get a C when you got a 95% on your test. Otherwise, other examples, let's say that height example again, it would depend on the population that you're looking at in terms of, okay, average height for males in this country is supposed to be like 5'10". So if we're talking about height again, it might change depending on the context, right? If I'm talking about the NBA, it might be a little bit different because the average height for an NBA player is actually like 6'7". So it'd be way over here somewhere. I don't know if this isn't to scale or anything. But different pressures, different populations have different distributions because of what's needed to survive, right? You can't live in the NBA if you're under 5'5". There have been very few players that were under 5'5" in the history of the NBA. Whereas I could take that and flip it to look at a different context, right? Normal distribution again. The average height for women in this country is somewhere around 5'5", but if you look at the average height for gymnasts, for women that are gymnasts, it's a little bit shorter than that, right? Again, not to scale by any means, but the average height for a gymnast is 5'1" or something like that. And it makes sense because lower center of gravity, it's going to be easier for you to flip and do all sorts of crazy stunts when you're shorter, right? Simone Biles, I think, is like 4'8" or something like that. And she's one of the greatest gymnasts ever. So obviously shorter is better in that case. So it depends on the context. It depends on the population and what pressure is applied to that population. But all these examples that I've done so far are technically examples for directional selection. You're eliminating one extreme or the other. But I have other videos that you're going to watch, and I'd like you to put those examples in these places. So you can draw in some directional selection, stabilizing selection, disruptive selection examples later. This was just an intro so you guys knew what that bell curve was and how we can change that bell curve depending on pressure. Right, so evidence of microevolution. All right, that's